Kia ora and welcome to this introductory video on light and sound. So stay tuned and I hope you enjoy and learn a lot about particularly waves and these two forms of waves. But first let's do a little bit of a recap. What is light? Well, light is a form of energy that we can see and is given out by hot objects. It is made up of waves that travel outwards from a light source. Some of the waves reach our eyes, but most continue elsewhere. So I use this word waves. Well, there are two main types of waves, and they are transverse waves and longitudinal waves. All types of electromagnetic waves, including light, as well as water waves, travel as transverse waves. Sound waves travel as longitudinal waves. We can see this, I should put my laser pointer on here, and is often demonstrated with slinkies. So, particle movement in transverse and longitudinal waves. Longitudinal waves, or sound, are compressing waves and are a compressing and expanding wave that needs a medium to travel in. A medium could be our atmosphere. A medium could also be any form of gas, solid, or liquid. Transverse waves, or light, are a moving wave where each part of the wave travels up and down, repeating motion as a wave forms and moves forward. Okay, see that there. These do not need a medium to travel through and can travel through empty space. Sound waves are mechanical waves requiring particles. And that is why you need a medium to travel through. Air particles vibrate backwards and forwards, creating repeating patterns of high, compressed particles and low, spaced apart particles, pressure. Sound travels in the form of longitudinal waves. One wave stretches from one compressed area to another, okay? And this can be through air, water, or a solid. One of my favourite sci-fi movies is Alien, and the caption for their posters was, "In space, no one can hear you scream." And that's true, because in space it is not a medium, it is a vacuum. There is no particles there, or very, very few, for sound to travel through. So all those cool Star Wars movies where you hear all the explosions in space would actually be absolutely silent. You'd probably only hear explosions if you were in the ship. So, we're talking about sound. Well, let's just have a look a bit at the biology. Well, sound waves travel through the ear canal. Okay, sorry, go back, ear. And then they cause the eardrum to vibrate. The small bones of the inner ear transfer this vibration, smallest bones in our body, to the inner cochlea. Okay, this bit here. The cochlea is a fluid filled and lined with many hair-like nerve cells that, when activated, send those signals to the brain. Different length nerve cells detect different wave frequencies, and they transmit this information to the brain using an electrical impulse that moves along those nerves. So here's the nerve bundle here that goes to your brain up here. So you might want to pause this video and maybe make a note of some of those important structures and how they work. So, the waves generated from an earthquake travel through the ground as both longitudinal and transverse waves as well. Primary or P waves are longitudinal waves and move the fastest. They are similar to the sound waves and can travel at 5,000 meters per second through solid rock. Longitudinal waves can also travel through liquid and gas, traveling at the speed of sound through the air. The secondary, or S waves of an earthquake, are transverse waves, and they can only travel through solids. They travel at nearly half the speed of our P waves. So you can see the two types of waves in an earthquake here and the damage that they could cause. So waves are a means of transferring energy from one place to another, without also transferring matter. Some waves need a medium, that includes matter, to travel through in order to transport their energy from one location to another, and these are known as mechanical waves, such as ocean waves, sound waves, and earthquake waves. Other waves can travel through a vacuum of space, where there is little or no atoms. These are known as our electromagnetic waves, and examples of those waves include light, microwave, and radio waves. Light and other types of electromagnetic radiation from the Sun and even further away stars travel through space in this vacuum. Light does not need matter or a medium to travel through. Each particular type of electromagnetic radiation, including each different colour of light, has a unique fixed wavelength called the wavelength here that it travels in. So you can see all the different wavelengths, red being the largest to violet being the smallest. Some objects, such as the Sun, release large amounts of energy. The energy can be emitted from the energy source in the form of electromagnetic radiation and travels in electromagnetic waves. Light, radio waves, and X-rays are all forms of this electromagnetic radiation and are displayed in this diagram here. You can see the wavelengths up here, how big they would be. Okay, so we've got radio waves almost as big as a building down to tiny gamma rays. The smaller the wavelength, the more energy they have. And that's why our gamma and X-rays are quite harmful to our DNA and cause mutation, because they can disrupt our DNA at the atomic structure, the atomic level, which is not very good. Okay. Small objects such as atoms, viruses, and light waves need to be measured using a very small unit called a nanometer. A meter can be divided into 1,000 equal parts. That's called a millimeter. So to go from meters to millimeters, you divide by 1,000. If 1 millimeter is divided into 1,000 parts, then we have a micrometer. So very small again. If we divide 1 micrometer into 1,000 parts, then we have our nanometer. So this is a tiny, tiny, tiny unit of measurement. It is 1/1000th of a meter. Wavelengths can be measured in meters or nanometers. The type of electromagnetic radiation can be determined by its wavelength. Here you can see this cool graphic that just shows you how small some of those things are. Waves have troughs, the lowest points, and crests, the highest points. A wavelength is the distance between the two closest crests, here and here. The amplitude of a wave is a measure of its height. The height is taken from the midpoint between the trough and a peak up to the top of a peak of a wave. A higher amplitude wave indicates a wave has more strength, and that a light wave contains more photons, little packets of energy. The frequency of a wave is calculated by the number of waves that pass a fixed point in a given amount of time, and this frequency is measured in hertz. You can see here into the diagram 2 different frequencies. Because all electromagnetic radiation travels at the same speed, then more waves of shorter wavelength will pass by a point over the same time as waves of a longer wavelength. The amount of energy in a wave depends upon the frequency of the wave. The energy of a photon can be calculated by multiplying the frequency by another constant called the Planck's constant, which is known in science with the letter H. This constant is named after the famous German scientist called Max Planck, who made many discoveries about light and how it also travels as particles called photons. A photon does not have a mass like matter does. It only contains energy. Planck's constant is 6.626 times 10 to the negative 34 joules per second. The value is so small because a photon is so tiny that there are so many of them within a light wave. This is how energy is transferred by a light wave. When waves are going through a dense medium to a less dense medium, for example through glass, they speed up at the boundary. This causes light rays to bend when they pass from glass to air at an angle other than 90 degrees. This is refraction. Beyond a certain angle, called the critical angle, all the waves reflect back into the glass. We say that they are totally internally reflected. All light waves which hit the surface beyond this central critical angle are effectively trapped. The critical angle for most glass is about 42 degrees. Fibre optics make use of this, so light rays can travel down a glass fibre that has curves in it, and that's how you can see around corners. So here you can see that angle reflects and changes when it hits the air. So if this is our glass, this is our less dense air, we come in and we bend. Okay. Light travels fast and in straight lines. At the speed of light, which is 300,000 kilometers per second, light from the sun takes about 8 minutes to get to us, traveling 149 million kilometers to Earth. Light can go around the Earth 7 times in 1 second. Light travels in perfectly straight lines until something bends it. The straight paths of light are called light rays. Light travels in a straight line until it strikes an object or a force. Light can be reflected by a mirror. You probably looked at one of those this morning. Refracted by a lens, so glasses, or absorbed by an object. If you've ever felt hot black tarmac on a hot day, you'll wonder why it has got so hot. Light interacts with matter by transmission, including refraction, which is travelling through it, absorption, where it enters but doesn't leave again, or scattering, including reflection, where it bounces off. So that's really important. To see an object, light from that object emitted by or scattering from it must enter your eye. All light rays travel through in straight lines. The image is not distorted when looking from the other side. Allows light to pass through, but the rays are, this is being transparent. All light rays travel through in straight lines. The image is not distorted when looking from the other side. So something that's transparent, you can see straight through it. Being translucent allows light to pass through, but the rays are scattered and the image can be distorted when looking from the other side. And finally, being opaque is that no light rays travel through and no image is seen from the other side. A shadow is a dark area that is formed due to light travelling in straight lines, which opaque objects block. An object that stops direct light rays creates a shadow. The shape of the shadow resembles the shape of the object that is opaque. The shadow created when the moon blocks the light from the sun to the earth is called a solar eclipse, and you might have been lucky enough to see one of those. The length of a shadow formed on the ground depends on the angle that the light rays hit that object. Blocking the light, if the light rays hit the object straight on, then this will create the smallest possible shadow. The greater the angle here the light rays hit, the longer the resulting shadow. The changing of length of the shadow can be seen as the sun moves across the sky. In the morning and afternoon, the shadows created are longest, as the sun has the greatest angle. The shortest shadows are formed at midday, when the sun is directly overhead, like in this diagram. So we know light is a form of energy, and the sun is the most important source of that light, which is produced along with heat energy, which we looked at in another video. That is transformed from matter during a nuclear reaction. Other sources of light energy, such as electrical lighting, fire, and the glow from bioluminescent animals, are produced during energy transformations that we've also looked at. Light sources need energy to be transformed to produce light. These are also called illuminators. Objects that appear to produce light, such as the moon or a shiny object, but do not use energy, are called reflectors of light. Light rays must originally come from a light source, such as the sun's light reflecting off the moon. So the moon is not an illuminator, it is a reflector. Virtually all of the electromagnetic radiation that arrives on Earth is from the sun. The sun is an incandescent light source because the light energy is generated from heat. The nuclear reactions that occur within the high pressure center of the sun release large amounts of heat. The heat causes the atoms that make up the sun to move around faster, As these atoms collide together, the electrons move up and down orbits around the nucleus and release photons of light each time they move. Each different type of element releases combinations of light in different wavelengths or colours, and this is called the spectra. We can read what type of elements make up the Sun and other stars as well by looking at what spectrum of light is emitted. And you look at this in physics and earth and space science in the senior school. Some animals can produce their own light through chemical reactions in their bodies. This light is known as luminescence. It is much cooler than incandescent light, as it does not require the heat energy to produce it. Glow sticks and fluorescent lamps also emit this type of light without producing heat, so are far more efficient to use than an incandescent filament light bulb. Throughout physics, you need to know how to interpret and draw these lights. We use this through ray diagrams. Ray diagrams are used to show an image of an object reflected in a mirror. Straight lines from the object are drawn towards the mirror, using the rule from the angle of incidence and reflection. The lines are then reflected back. Arrows are used on the lines to show the light ray's direction. We're going to unpack this now. The main rule for mirrors is that the angle of incidence, so the angle that the light comes from, is equal to the angle of reflection. That's really important. So this angle here is equal to this angle here. This means that the angle of the light rays between where it arrives and the perpendicular line, the one that reflects, this one here, sorry, the perpendicular line, that's the normal, to where it hits on the surface of the mirror is the same angle it leaves and the same perpendicular normal line. Unknown angles can be calculated using the rule for mirrors that the angle of incidence equals the angle of reflection. You need to know the normal line is 90 degrees to the plane and that the mirror and all angles A, B, C and D must add up to 180 degrees. You can see this calculation here. Pause the video now and try and work that out yourself. When you look directly at an object, you can see where it is. But if you look at it in a mirror, when you are looking at a reflection of the object, the image is behind the mirror. An image in a view of an object at a place other than where the object is. Images can either be real or virtual. A real image occurs when the light rays pass through the place where the image is, for example, the image on a cinema screen, or the image that falls on film in a camera. A virtual image occurs when the image appears to be at a place where the light rays do not pass. When you hold an object in front of a mirror, the reflected image you see is behind the mirror. Obviously, no light can come through the mirror, so the image must be a virtual one. All reflected images of flat surfaces are virtual images. Images in a plane mirror are the same size as the object, the same distance behind the mirror as the object is in front. Virtual, light that does not really go to them. Laterally inverted, the left side is swapped to the right side, and the right side is swapped to the left. So this is the virtual image that you see. It is the same distance as the original object. It is swapped, so we've got the almost opposite image that you can see there. Mirrors work because light is reflected from them. The three types of mirrors are plane, concave, and convex. The images in the plane mirrors are the same size and the right way up, but laterally inverted, and is a flat reflecting surface. The image in a concave mirrors are magnified and the right way up when you are near to the mirror, smaller and upside down when you are further away from the mirror. The images in a convex mirror are reduced and the right way up. Here you can see the light rays we draw in, the rays of incidence and the reflected rays. This focal point determines whether or not the image is upside down. If you look on this side of the focal point, the image will be inverted, upside down. If you look at the image here, it will be the right way up. It will still be distorted. The opposite goes for convex. They will make things larger. Okay. Typically, 3 rays of light are drawn reflecting off a concave mirror. The center incident ray flows from the principal axis, which travels straight into the center of the mirror. The reflection ray travels directly back on the same line, and another incidence ray of the light parallel to the principal axis is drawn, and the reflected axis reflects inwards. A normal line can be drawn where the ray hits the mirror, and the incidence ray equals the reflected ray, where the rays cross at a focal point, which is F here. A third incidence ray can be drawn on the opposite side of the principal axis, with the reflected ray crossing the focal point as well. Very similar in a convex mirror. We've got the incidence ray coming here being reflected, okay, and the normal is between those two. Okay. There are many uses for mirrors, beauty mirrors or shaving mirrors, so you can get a nice close-up of your face. Security mirrors, so you can see round corners and bending light. Lenses are different to mirrors as they change the type of medium the light flows through. Here we can see what we looked at before. When light travels through an object, the medium changes and the density will cause the light to bend. And when it changes the medium again, it will continue at its original angle. Here you can see as well the angles of incidence and the angle of reflection are not equal in prisms. In a convex lens, our light converges, so it amplifies the energy into one point, and you may have seen this. You can burn paper with magnifying glasses, and here it spreads out the light, which allows you to light up a larger area. So you might see this in torches. We can still draw our light by using our lines here and our arrows to indicate which way the light is traveling using our ray diagrams. And here you can see convex lenses. We also have a focus here, and that is the point at which the light is most focused. Again, how to draw these, we've got extra information we can add. Focal length, not too important at junior level, but still extra information if you want to use it. Finally, here we have our optical axes and our principal focus, and we have our ray diagram of a concave lens here. So there we have it, a lot of information to send to you. I hope it all makes sense. Again, take plenty of notes, come at me with questions so I can clarify any misconceptions you may have. I will catch you in class.